All right, folks, welcome back to Start 445 Regression Analysis. I will continue with the inference really quickly, and then we conclude on lecture 3. I hope you enjoyed the previous lecture talking about inferences, hypothesis testing. We talk about the trend test, the F test, and then the individual test using the T test. Okay, if you have questions, you ask me in class. So we talk about confidence interval, okay, which is something you are familiar with. So we didn't spend much time. So this is just showing us a 95% confidence interval because the critical value is what, 0.05, and then the probability that the true parameter is sandwiched between these two numbers is 0.95, okay? So this is our confidence level, 0.95 or 95%, and our significance level is 0.05. Okay, what's important is to know how to interpret confidence intervals, and we'll practice one or two in class, or even here actually. So the bounds of the interval are random. Okay, remember beta j hat is a random variable. Okay, the estimator that we use to get this is a random variable. And in other words, depending on the data we use, we will get different bounds. Okay, that's why we say it's a random. The bounds are random. Okay, if you are using data from BAM library, you get different bounds from if you're using data from Volta Hall or Mensa Saba and so on. Okay, we are saying that in repeated samples, the interval that is constructed in the above way will cover the population regression coefficient in 95% of the cases. A lot of the time, people will say we are 95% confident that the true parameter, okay, lies here. Okay, so that's it, what people say, but I prefer a better way, which is more accurate. Okay, now this one is a true parameter. It exists. You are not going to use the language of will lie. It's not going to lie anywhere. It's already existed. It's up to you to cover it with your interval, or you cannot cover it. So that's the language here, that in repeated samples, if I were to go to BAM library, collect data, construct this confidence interval, use the same approach. This is BAM library. Go to Volta or collect data on students, construct a confidence interval, go to Bush Canteen, go to, so assuming this study is about Legon, University of Ghana, and then go to Equafo Statistics Department. If this construction is done the same way for repeatedly, or if it is done 100 times, okay, 95 of those 100, okay, of 95 confidence intervals out of the 100 I have just done will cover the regression coefficient. That's the idea. If I were to repeat 100 times, 95 of them will cover the population parameter. So I'm saying the parameter exists already. You will cover it or not. So we don't like using the language that this rather will go and lie in an interval. No. So this is the clear, precise language. In repeated samples, the interval that is constructed in the above way will cover the population regression coefficient in 95% of the cases. Okay. So this here is just showing you that we can have 1%, 99% confidence level, 95%, and 90%. All depends on the critical value you are using. Okay, and you read this on the chart, the T table. Okay, so the confidence level or significance level will tell us the kind of confidence interval we are constructing. Okay, so it's easy to construct. You don't need to memorize anything. Always, it is what? Let's say it is always going to have the true here. Okay, always is easy. Is the true here. Then you are going to have the estimated here minus something, the estimated here plus something. And what you are adding and what you are subtracting are the same, right? T, let's say alpha over 2 and minus k minus 1. And then we have standard error of the beta hat. You put the same in. So that's what we have said here, that when you, the one you read on the table, okay, is, let's say, T times standard error. So it should be fairly easy to remember. Okay. All right. So let's go. If we were to run this in a regression and to use to test, okay, so this is just saying a rule of thumb that most students are familiar with this, so that they don't have to be reading from the table over and over. 5%, which we'll use often in this class, when you read on the table, will be 1.96. Okay. And then C at 10% will be 1.645. Okay. Remember, the higher the significance level, the smaller the number. Okay. Now, there's something interesting here. You will learn that alpha j belongs to, if I hypothesize H naught that beta j is equal to alpha j, and alpha j does not belong to the confidence interval, then I have to reject H naught in favor of H1. And you will see an example. Okay, the next slide. So these are the two examples. A regression is run. We want to test R&D. Okay, this is research and development expenditures that a company expends. And we want to test for these sales here. Yes, you can see this one is like the beta hat. And you are plus or minusing the critical value times the standard error. Standard error is here. Okay, so this plus or minus is showing where you have beta hat minus something something and then beta hat plus, right? So there's plus or minus at the end. So that's a plus or minus. Now, what are we saying? This is it. What is H naught? The parameter here, let's say this is beta 1. It's supposed to be beta 1 in the population. Beta 1 is 0. And then H naught, H1, beta 1 is not 0. Remember, to reject H naught and so on, you're going to calculate your T, blah, 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 and then reject H naught if T calculators. We are saying that you don't need to do all that. If you have the confidence interval you should be able to make such a conclusion to reject H naught or not. So pay attention. That's what we are saying here. Look, so we are saying that this confidence interval has been constructed. If you look at this thing here, this thing doesn't contain 0. It starts from 0.961, 1. So there's no 0 here. But once this begins with a negative number and ends with 0 point something, the number 0 is contained in this interval. So here you fail to reject. Think about it. I'm hypothesizing that beta 1 is 0. Now, a confidence interval for beta 1 contains 0. So I cannot be rejecting this guy. No, it's not, it doesn't make sense. I'm hypothesizing that it is 0. I constructed a confidence interval which is supposed to contain this true value. And that confidence interval contains 0. So I cannot reject H naught. But over here, I'm claiming this thing, I'm hypothesizing it is 0. But when I constructed confidence interval, which is supposed to contain it, this thing doesn't contain 0. So I have to reject this guy. So that's how we use confidence interval to reject, okay? And the note is here, okay, to help you. So if a confidence interval contains 0, you cannot be rejecting that the true value is hypothesized to be 0, no. Okay. Now, sometimes we want to construct confidence interval not only for the true parameters, sometimes for the mean response, okay? So it's going to be straightforward. Look at the middle. That is what we are constructing confidence interval for, the mean response. The mean response, okay? Remember that the mean response is always like this. Expectation of y condition on the point, the mean response at the point is x0. The mean response is always what? X beta. So here in the textbook that I picked this from there, they use X transpose beta, but we have been using X beta. That's fine. So the mean is always like this, okay? And we are saying that, okay, an unbiased estimator of this mean response, okay, is this guy. For example, take expectation of is here. Take expectation of y0 hat. This is what you get. Okay, and if our y is equal to x beta plus u. Okay, this is just to demonstrate. Expectation of y condition on x is just x beta. And then when you take the expectation of y0 hat, okay, they are the same. Okay, in this case, let me use what the textbook is using. We are saying that this thing here that we want to find confidence interval for, it looks like this. And if you were to take y hat at that point and take its expectation, it looks like the same thing. So this is an unbiased predictor. And therefore, it is the one we will start with. I mean, the y0 hat. Y0 hat is an unbiased predictor of this thing here. Remember, if beta hat predicts beta, or the expectation of beta hat is the true, then you have the true here, and the unbiased estimator begins the confidence interval, right? Sorry. It is the unbiased estimator that begins and then minus the correction term plus the correction term in constructing confidence intervals. So that's the idea here. The idea here is that, look, this thing here, if it looks like this, if it takes its expectation, this is how it looks like. And this thing here, if you take its expectation, this is how it looks like. Therefore, we will start with what we want to construct confidence interval for in the middle. An unbiased estimator of it is this. Then we add the margin of errors term. That's all. So we do plus and minus. Now, you know where this comes from. This is read from the T table, right? This is our n minus k minus 1, which is the same as n minus p. Now, what is the variance? Remember that in the confidence interval we just studied, we will use standard error of beta hat over here, okay? Because we were starting beta hat. Therefore, what is the variance? What is the standard error of y0 hat? The one we are using, the unbiased estimator of this one. This is an unbiased estimator of this. So we are using its variance, just similar to what we did earlier, actually. So standard error will be what? Square root of y0 hat. So square root of the variance. So what is its variance? Variance of x0 prime beta hat. Remember, in matrices or in the elementary, I keep showing you this. Variance of a constant times x is a constant squared variance of x. but we cannot be doing square of a matrix. So you write it in a nice way, okay? So this will come out as what? X0 transpose variance of beta hat and X0, okay? Still in the square root. That is it. The X0 is the one here. X0 prime is the one here. Variance of beta hat, we have derived it, will be sigma squared X transpose X inverse. So that's where it comes from. If you are giving all these numbers, you should be able to construct confidence interval for the mean response, right? Once you look at what is in the middle, then you know what we are constructing for. It's an interval for the mean response. Remember, if you have something like this, beta hat plus the margin of error, then this is minus the margin of error, beta hat. You look in the middle. So this is a confidence interval for beta. So this is a confidence interval for the mean response. Similarly, we can be asked to construct a confidence interval for new prediction. Prediction of a new observation. Okay, I beg your pardon. A new observation. So there is a y coming in the future, or y0. I want to have a confidence interval. Where will it fall into? Okay, what bounds cover that future observation? So once you look in the middle, there is a confidence interval for a new observation, y0. Okay, similarly, of course, we will use what we have predicted for it. Okay, what we have predicted for it is what we are going to use. Okay, but here we change the margin of error because it's forecasted. We rather take the variance of the difference of what it will be, okay, and what we are forecasting for it. Okay, these are assumed to be independent. So you will just have variance of y0 plus, okay, variance of y0 hat. This we have derived in the previous slide. That will be to be sigma squared. No, this one, of course, will be sigma squared plus this one, variance of a future observation, any of the y's is y sigma squared, remember. And this we have derived just on the previous slide. That will have x0 transpose x transpose x inverse x0. Then, as you can see, you factorize sigma squared out, you get 1 plus x0 transpose x inverse x0, okay, as is shown under the root. Now, don't be confused about the introduction of the x0. Remember, we use x for all the x's, but now we are choosing an x from a list of x from the x's. So in our returns to schooling, maybe you have a constant and the value of education is here. Value of education, a particular education, then experience, then tenure. So we cannot call this particular element. The star means at particular levels. We are just calling them x0. But all of them for all the data points will be capital X. But we are isolating a case where there's a constant, maybe education is 5, experience is 8, tenure is 7. We are isolating a particular point from that vector. That's why we are calling it x0. And that's what we are doing, prediction of new observation at a particular point like this. So this can be your education, number, experience, and so on. So remember all these formulas. Okay, now let's talk about simultaneous confidence interval. Sometimes you have to construct, remember we all know how to construct 95% confidence interval for beta 1, for example, in simple regression, and we can do same for beta 0. Okay, so 95 for this separately, 95 for this separately. What's the meaning of simultaneous? At the same time, okay? Can we construct simultaneous confidence interval where we say that at the same time, it is true for beta 0 and beta 1. Okay, remember we can do separate ones, 95 for beta 1, and we conclude that 95% of the cases, the interval covers beta 1. Fair enough. Can we have intervals where we are sure that 95% it is true for beta 1, and 95% it is also true for beta 0. It turns out that if you were to do separate 95 and separate 95, it may not be true that jointly it is 95% true that this interval covers beta 0 and beta 1. This is the idea. If you do 0.95 for beta 0 and 0.95 for beta 1. So a joint confidence interval says, okay, 95% true for beta 0 and 95% true for beta 1 jointly. Okay, can you have two intervals? We can have an interval for beta 1, interval for beta 0, and say we are 95% confident that beta 0 lies here, beta 1 lies here. That's what we are talking about. We are not saying, oh, individually, 95% confident that beta 1 lies here. Okay. And then we are also confident at 95% that beta 1 lies here. Okay, beta 0 and beta 1. We are not talking about separate 95. Can you confidently at the same time, simultaneously, jointly, those intervals contain a true parameter? The idea is this: if beta 0 is here and beta 1, you have 95% for this, 95% for this and that. When you multiply them, it's approximately 0.90. It's not 95%. So if you have separate 95% for beta 0 and beta 1, then you are actually saying that at 90%, this is true and this is true, where they are at the same time true simultaneously. Okay, at the same time true. So it is not true that whenever you construct 95 separate, then you are 95% true that this is true and that is true. Keyword is and. Probability n means multiplication, right? So if you construct 95, you get 0.90. Okay, so it's not true. So this is the note here. Some problems require that several confidence or prediction intervals be constructed using the same sample data. In these cases, the analyst is usually interested in specifying a confidence coefficient that applies at the same time to the entire set of interval estimates. A set of confidence or prediction intervals that are true simultaneously at the same time true. At the same time, that 95%, this is true for beta 0, this is true for beta 1. I've told you if you were to do separate 95, it can only be 90% true that both are true at the same time. Okay. All right. Remember that we said in repeated sample, what you get here will be different from what you get here. So as you keep doing, okay, or even with the same sample data you are doing for beta 1 and beta 0, when will you be sure, okay, that at the same time it is true for both? Okay, we call them joint prediction intervals. Joint confidence, or joint prediction intervals. Okay, so that's a basic idea. So to make them all true at the same time, okay, I don't want to go through this. We start with the estimate and plus or minus some errors. Okay, there is a method called Ben-Foroni that helps us to choose the delta. Ben-Foroni approach to simultaneous inference in linear regression. Okay, in this approach, that delta, the error margin, is chosen to be alpha over 2 times R. R is the number of parameters you want to jointly construct a confidence interval for. Remember, we have beta 0 and K other parameters making our P. So we have P, but how many out of the P do you want to have a joint confidence interval for? That is R. Okay, so R is always less or equal to P. Either you are constructing for all the parameters or a subset, which we call R. Okay, so there's an intuition here which I would like to highlight, and then we move on. It says that For example, if you want 90% joint confidence interval, that's what this formula is saying. Rather construct 95 for each. So assuming it is beta 0 and beta 1. Okay, in a simple regression case. If you want 90% joint confidence interval, that beta 0 lies here and beta 1 lies here. Okay, at the same time, 90%, do 95% for each. And I've demonstrated to you that 0.95 times 0.95 is approximately 0.90. In other words, if you actually want a 95% joint confidence interval, what is this joint confidence interval? Please be clear that beta 0 lies here, and at the same time, beta 1 lies in that interval you've created. So you have two intervals. You are saying beta 0 lies here for sure, 95%. Beta 1 lies here for sure, 95%. At the same time, remember, you can have an interval, it is true for beta 0, but not true for beta 1, and so on. Or they are true, but not at the same time. But for you to say it is true for this and true for that at the same time jointly, if you want to say 95%, then construct 0.975 confidence interval for both. And we are talking about simple here. If you multiply this on your calculator, you will see that it's approximately 0.95. That is all this formula is saying. Okay, that if you want 95% joint confidence, rather do 0.97. So that this is true and that is true, you get 95%. Okay. The last slide before I end this particular set of video. Why will regression coefficient have the wrong sign? Sometimes you expect a beta j hat to be positive, but it turns out that it's negative, and vice versa. What are some of the reasons? One, the range of some of the regressors is too small. The range of your regressor, we've said that we need more variation in our regressors, more variation, and so on. If the range is too small, you don't have enough variation to actually estimate the true sign, okay, of that parameter. Now, if you leave out important regressors, remember we've talked about the consequence of omitting relevant regressor is that you can have bias estimate. Yes, it can be so biased or inconsistent that the sign also changes. Now, if multicollinearity is present, you can have wrong regression coefficient signs. Of course, computational errors. If you are using some software and there are computational errors, okay, or manually doing something, you could have wrong coefficient. Okay, so I'll bring this recording to an end and continue on the next video. I hope you're enjoying the class. Thank you.